Till now we have been discussing the cases of systems capable of oscillation when the system is disturbed from its equilibrium position and subsequently allowed to oscillate freely of its own, and that is why we call them free vibration. The primary objective of that kind of an analysis had been to find out the frequency with which it oscillates of its own, that is what we call natural frequency. The importance of that comes from the fact that, as you will see very soon, that any kind of situation where an external excitation matches in frequency with the natural frequency of the system can result in disastrous consequences, and that is why it is better to know beforehand that what is the natural frequency of a system, and so that it should be such that it never comes anywhere near the frequency of any kind of excitation the system is expected to be subjected to. Now in this lecture we will start the cases which is far more encountered in our engineering design, that when a system is excited by an external agency, then what will be the response of the system when it is subjected to this external excitation. So this we call forced vibration, and again, to keep our discussions simple at the beginning, we take up a single degree freedom system subjected to excitation force. Now, we should also beforehand know that forcing, what does it mean? So, excitation of a system can be of various types. First of all, we will classify the situations according to the nature of the forcing function or the disturbance. If the forcing is purely a harmonic function of time, like say if we call this is the force, so this is called harmonic excitation, because the excitation, the function of time, is a harmonic function of time. But before that, we should classify in general as excitation as periodic, that means where the forcing function is a function which repeats itself after a fixed period. So this kind of excitation which repeats after a fixed time, which we call time period, is called periodic excitation. Another kind of excitation can be aperiodic. Aperiodic excitation can be anything like this, which does not repeat itself after a definite time, that is called aperiodic. And there is a very special case which we will not be able to discuss, but nevertheless very important, called random. there are many cases where the excitation is of random nature, which has certain special characteristics. What is random? But we will not go into those things, because we will keep our discussions into to the simplest possible situations. However, this periodic excitation can be further classified, as I was mentioning initially, to case called harmonic, other is anharmonic. Say the second one, it is periodic, but it is not a simple harmonic function of time. The classification of excitation can be again done from a different point of view. Here we have been doing it from the point of view of the nature of the excitation as a function of time. The other way of looking at the classification problem is that what is the manner in which it is excited. For example, I can take this and try to vibrate by applying a force. Sometimes a system can be oscillated or disturbed by applying some kind of a disturbing motion to its support or the wall to which it is connected. Sometimes a system vibrates by itself. Only thing that we have to supply is source of energy. Sometimes it is excited by a periodic variation of one of the parameters, either stiffness or inertia or something. So there is another way of classifying excitation. Based on the fact that where from or how it is being excited. So there we can have force excitation. The other one where the support on which something is resting is called, and that is oscillated, that is called base excitation. Other one is self excitation. And there are cases, of course, which we call parametric excitation. So therefore, our problem of forced vibration can be any kind of combination. It can be a periodic anharmonic base excitation problem. So what we should do, as always it is advised, to take up the simple possible situation. We have taken the simplest system, an undamped single degree freedom system, but vibration now, excitation also will take the simplest, that we will take harmonic excitation, and the excitation is given in the form of either a force or a moment. Another reason why harmonic excitation is a very important problem, that any kind of periodic function of time can be represented in terms of a Fourier series where each term or component is a harmonic function of time. And as we are dealing with only linear systems, so if a particular forcing function gives to a response x1, and another forcing function f2 gives solution x2, then when both are combined, then they will give the response x1t plus x2t. This is a very important result, but valid only for linear systems. So therefore, if this periodic function of time can be split into a series of harmonic functions of time, then for each harmonic function of time we can get the response, and so the resultant response will be the sum total of all the responses. So therefore, if we know how to solve the problem for the case of a harmonic excitation, we can solve for all periodic functions of time. Even aperiodic functions of time can be represented in terms of an infinite Fourier transformation, and there of course it will be not the discrete frequencies, but there the frequency spectrum will be continuous, and we will see such cases, but the resulting the conclusion is that even this problem can be solved using the result of the system's response to a harmonic function, because this can be also represented in terms of harmonic functions of time using Fourier transformation. So therefore, if we are handling linear systems, knowing its response to harmonic functions of time can give the result of any type of forcing. With this little introduction now, let us solve the problems one by one. The first we will take up the case of a undamped system with single degree of freedom, which is excited by a force that is a simple harmonic function of time. It's a very simple problem. Let us find out the value of or the expression for x, that is the response of the system. Now at any instant of time, the forces acting on this will be kx So total acceleration in this direction x2 dot multiplied by m has to be the total force in that direction, that is or so this is the differential equation which we have to solve now, and we all know that the solution, general solution, will have two parts. One is the complementary function, that is the solution of the homogeneous part of this equation, that is mx2 dot plus kx equal to 0, and plus the particular integral, which for this case we have to find out. So the complementary function, that is the solution of x to the homogeneous part of the equation, is we know that already from our previous lectures. So this is the complementary function and this is the particular integral. Here of course omega n is again the natural frequency of the system. We also define another quantity R, that is the frequency ratio given by the ratio of the forcing frequency with the natural frequency. Now these constants A and B will depend on the initial condition. So initial conditions mean what is the starting velocity and position. So, let us now try to solve this problem. So, we know x t is equal to a so x dot t will be and let us consider a relaxed condition to begin with. So, at t equal to 0, let both x and x dot be equal to 0. Now, this is something which is possible in forced vibration. In free vibration, if we give initial condition as x and x dot both 0, system will continue to remain at rest. But since now we are disturbing the system, it will oscillate. So, putting this, what we get is 0 equal to b plus and if we put t is equal to 0, x dot equal to 0, 0 equal to. So, the two conditions we get a equal to 0 and b equal to minus and the solution becomes this can be written in a slightly different form. This pure trigonometric manipulation. So, this is our final solution, that how a perfectly undamped single degree freedom system will respond to a purely harmonic forcing function like this. So, let us, if we plot it, so let us plot it and so now one thing we can find So this is a constant for a given value of r, or r is nothing but omega by omega n. Now this is again a harmonic function of time where the frequency is almost approximately equal to omega, because this when omega n not very different, it will be something like that. On the other hand, this is another harmonic function of time which is changing with a very lower frequency, because it is the difference of the frequency. So in a crude manner we could say that this is a harmonic function of time where the magnitude or amplitude fluctuates slowly with this form, and that is how we are getting so the fluctuation of the amplitude is a slow process with a time period 2 pi by omega n by omega. This whole thing will be when it completes 1. And this fluctuation phenomena is known to you perhaps, which we call beating, and the beating period is this one. Now one thing we see, suppose what happens when we start from a low value of omega. Omega is nearing 0, that means r is nearing 0. So this will be approximately 2f0 by k, and this will be approximately sine omega n by 2, and this will be more or less same. But what we find here is that as omega increases, that approaches towards n, when r approaches 1, what happens to the beat frequency? Beat frequency is this. So when omega approaches omega n, beat frequency or beating period approaches, since beat period is 2 pi by this, the beating period will approach infinity. Another thing we find that the amplitude, the maximum value to which it fluctuates, it depends on this quantity. And here when r is approaching 1, then this is gradually exploding, and amplitude which depends on this, that also approaches. And so therefore, if we want to plot this under this situation, this is a case where r is equal to 1. What we will get? We will get can be shown, this angle is tan inverse, and of course this is still so now we find that when r is equal to 1, that particular case beat period is infinite. That means it never comes back, it keeps on increasing. The maximum value to which this we reach also keeps on increasing, and it can be shown mathematically. We will not go into those things, that this amplitude will keep on increasing linearly, and the rate of increase can be decided by this angle of the tangent to the various things. So, this particular phenomena, what is going to happen then if such a system is there, then it will keep on increasing in its oscillation amplitude indefinitely, and that is what we call resonance. That is why now we should remember our earlier caution that a forcing function, when it is acting, we should be careful that the forcing frequency never really goes anywhere near the natural frequency of the system. That is why when something is being designed, its natural frequency should be estimated, and it should be ensured that the system is never subjected to a kind of forcing function or excitation where there is a chance of resonance. And these are the kinds of things perhaps you have heard, that when a military marches through a bridge, this left, right, and normally on a solid ground they keep on marching all in unison. That means everybody is in phase. But once they cross a bridge, they are always told not to be in phase or unison, and they are not supposed to march. They walk through that, because in case all these hundreds of soldiers, they keep on marching with the same frequency, same phase, then the forcing function will be enough, and it can match the natural frequency, at least go somewhere near the natural frequency of the bridge, and it can cause disasters. And therefore, this is the point which we wanted to. But the common view that which is held sometimes, that if the resonance takes place, there is amplitude of vibration is infinity. It is not so. Actually, what happens in resonance, that the intensity of vibration keeps on increasing indefinitely. If you allow infinite time, if the system is capable of taking infinite deformation, it will go to infinity. But really what happens, that this system gets damaged because of large scale oscillations taking place. However, this is a very idealistic situation, because in nature it is impossible to make a system which is absolutely free from any energy dissipation. Therefore, to make our analysis somewhat more realistic, what we can do is that even if we consider the system to be notionally undamped, that means we do not show a specific damping agent there or damper, but still we have to keep in mind that there is certain amount of dissipation. It may be very small. And so in reality what happens, that this, even the very minute amount of damping present in a system will damp out the complementary function or the free vibration part. And how the response will look will be this. Of course, I have shown this takes a short time, but in reality it may happen that it will continue for a large time, but eventually the initial free vibration part, that means this is the free vibration part, that will gradually damp out, and what will remain is only the complementary only the particular integer. So the response in the steady state situation, that means which will keep on maintaining its nature and character, that is called the steady state. So this in steady state, the solution or xt is only the particular integral part, because the natural vibration part which was represented by the complementary function has gradually died down. That is the response, and this is what we call transient. It is a passing phase. So this does not repeat itself. After it reaches the steady state, there is no further change, and there the response is this. So in general, our primary concern is the response of a system in the steady state, which in this particular case happens to be this. Of course, R is not equal. Now you see this f0 by k, here we find that it is again the forcing function is cosine omega t f0, and response is also similarly some quantity into cosine omega t. So therefore, if we plot in the steady state, response will look like this. If we plot both x and the forcing function in the same graph, so it will look something like this. And the response will look where the magnitude of this is f0 and magnitude of this is f0 by k. This is the situation when R is less than 1. When R is more than 1, then what will happen? Then, or this case, x will be like this. I want to keep this always a positive quantity. So we can write this as r square minus 1 and take minus sign here, and we can write this as so. Therefore, what will happen now, that the forcing function and the displacement of response, they will be just out of phase. So, when the forcing frequency is above the natural frequency of the system, that is R is more than 1, then the response will be out of phase by 180 degrees of phi as indicated in this. Now, this quantity f0 by k, what is this? This is nothing but the static deflection of this if I apply this force, that is f0 statically. So, f0 by k is the displacement of the mass from equilibrium if the same load applied in a static way, not dynamically. On the other hand, if the same force is applied dynamically, the deflection or the maximum deflection of this is nothing but the amplitude of oscillation, which is f0 by k divided by x quantity. So, for this, that means this ratio, the amplitude of oscillation, which is nothing but this, divided by the displacement, which is static when the force is statically applied, is, and we take its magnitude only, that is x divided by f0 by k magnitude, and this is nothing but as can be seen here. This is x. X divided by f0 k is nothing but 1 by 1 minus r square. This is called m, or magnification factor. It means that when a load is applied dynamically, the displacement of the system gets magnified compared to the situation when the load was applied in a static manner. Now, how this looks like, this magnification factor? This magnification factor, when we plot as a function of r, so it starts at r is equal to 0, magnification factor is 1, r is equal to 1, it shoots up to infinity. Again, when r is more than 1, it will become negative, but we are taking only the mod, so therefore it becomes positive, and it asymptotically approaches 0 as r tends to very large values. Of course, if we just want to plot the ratio of the amplitude with the static deflection, then when r is less than 1, x is positive and this quantity is positive, it goes. But when r is more than 1, then obviously x is negative because this quantity is negative. So, now, but if you take the mod of this, then we get back. So, this is called the steady state response of a system, single degree freedom undamped system, which the response characteristics is indicated by this plot, where the magnification factor or the amplitude at a particular frequency is given. So, and for the whole range of possible frequencies, or the possible frequency ratios are, the magnification factor has this kind of characteristic. So, this is the simplest situation which we have discussed. Next, I think if we have to take up more realistic cases, what we will do is that we will now consider a viscously damped system and subject it to a harmonic force. So, we will now take up a more realistic case where there is some certain amount of damping, viscous damping present, and again we will subject it to a simple harmonic function of time as the force, the harmonically excited system. This is the situation. Our lumped parameter model with viscous damping, stiffness, mass subjected to a simple harmonic force, a harmonic function of time f0 cosine omega t. The equation of motion we can write without going into again the free body diagram. We can write is going to be now not 0 as in case of free vibration, but the external forcing function. Now, we have seen, and we can keep it in mind, that any kind of response of a system, simple system, to harmonic function or harmonic force like this will be also again a harmonic function of time with the same frequency. So, this is a principle which you should keep in mind, that the response to a harmonic force will be a harmonic function of time with the same frequency. That is the only thing which you have to keep in mind. But before we go further, we will write it in a slightly different form. So, we can write this as or dividing the whole thing by m Now, C by m can be written as C by Cc, that is the critical damping coefficient, into Cc, which is nothing but in this particular case 2 Km by m, and that is equal to zeta damping factor into 2, and root over Km by m is nothing but root over K by m, that is omega m. Similarly, K by m is omega m. So, this equation can be again written in this form: x2 dot plus 2 zeta omega n x dot Now, this solution we can always write, let the solution be a harmonic function of time with the same frequency, that is all. So, we can write x is equal to x, capital X, that is the amplitude, cosine. Now, a function of time, harmonic function of time with same frequency, but there is no guarantee that it will be with the same phase. So, we cannot write cosine omega t here, rather what we will do with a different phase. That means so you can see that this is again a harmonic function of time, the response, but not at the same phase as this, as we had in case of undamped system. So, this is the most general situation, and I think there should not be any problem with this. So, this is the response. Only thing our job will be to find out the magnitude of the amplitude x and the phase difference. That is what we wanted to do. What we will do now is we substitute this solution which we have assumed into the equation. So, substituting the solution in equation what we will get x2 dot. If we differentiate this twice, what we will get minus omega square x cosine omega t minus phi into, there is nothing else. So, therefore, this will be the first term plus minus twice zeta omega n omega this is x dot multiplied by 2 zeta omega n. X dot is minus omega x sine omega t minus phi, and we have multiplied plus and this is equal to so therefore, we have converted the differential equation into an algebraic equation, but we have to solve for two quantities, one is x, other is phi. The technique is generally that we will see the on the both sides of the equation, the coefficient of cosine omega t on both sides must be same, and coefficient of the sine omega t on both sides of the equation should be same. So, if we split this, that means when we split this, what we will get minus Now, if we want to equate the coefficients of cosine omega t on both sides, what will be the coefficient of cosine omega t on this side? It will be minus omega square x cosine phi plus 2 zeta omega omega n x sine phi plus omega square x cosine phi. This is the coefficient of cosine omega t on the left hand side, and that must be equal to the same in the right hand side, which is x0 by m. Now again we have to equate the coefficient of sine omega t. So and the coefficient of sine omega t on the right hand side is 0. So from this we get, if we take sine phi and cosine phi, we get tan phi is equal to zeta omega and if we divide the numerator and denominator by omega n square, what we get 2 zeta r, that is the second equation. The first equation will tell us x is equal to so we take x common and divide f0 by m by the coefficient of x. So now if we take cosine phi common outside, we get f0 by m by cosine phi. If we take 1 by cosine phi is omega square minus omega n square plus 2 zeta omega omega n. So tan phi is already determined, is 2 zeta r by 1 minus. Now cosine phi we can easily find out. Cosine phi is equal to 1 by sec phi, that is 1 by square root of 1 plus tan square phi. Now tan phi has been already determined, so if we substitute this here again, finally x we will get as after simplifying we get this. So this is the response. Response requires two things to be given. One is the amplitude, which is this. The frequency is same as the forcing frequency, and the phase difference, the characteristic looks like this if you plot it. Magnification factor again we define the same way, the x by f0 by k, and as you can see, when r is tending to 0, then it is simply, this is 1, this is 0, so it will be 1. This way now of course you have a parameter like zeta. For different values of zeta, we will get different response. So zeta is increasing in this, and this is zeta equal to. Similarly, that is so far as the magnification factor. Phase difference characteristic. So if zeta is very small, it will be like this. Now as zeta gradually increases, and so on. So zeta increases, and this is the case when zeta is 0. Now there are two special cases where this is where it is tangential. This is a special value of zeta which is 0.707. Same thing, this is zeta 0.707. There we will discuss about these things later. So the frequency response characteristics of a viscously damped system is like this. Now it depends on the magnitude of zeta. The peak value is now restricted, it is no longer infinity. Even at omega is equal to omega n, it is no longer infinity. And the peak value is also not coinciding with r is equal to 1, gradually it is shifting. And for r is equal to, or for zeta is equal to 0.707, the peak value of the response is at r is equal to 0. That we will prove later. So therefore this is the general characteristics. Here again we find the phase difference is always 90 degree at r is equal to 1, and it is asymptotically approaching pi. So this is the situation. What we will do next is to look at this problem from a different angle using a different approach, which we will be taking up in the next discussion.